What is the direction of force on a beam of positively charged ions that enter the magnetic field from the left? We have a few options: up the page, down the page, into the page, or out of the page. Now, if this were an electric field, it means that the positive charged particles, like a positive current, would be deflected in the direction of the electric field. Because it's a magnetic field, that's not going to happen. Our answer is either going to be up the page or down the page. Which one? Well, we can use the right-hand rule. If our fingers are the magnetic field going into the board, and our thumb is the direction of the positive current, that is that way, then we can see that the force is going to be upwards. So our correct answer is A, up the page. Question 2. In which direction does current flow through the wire as the rod AB is moved up the image at a constant rate? Is it clockwise, anti-clockwise, alternating, or will there be no current flowing? So to answer this question, we need to look at what's happening to the magnetic field inside the loop, right? Now, the top of this loop is not inside the magnetic field. That means that when this rod is moving upward, the amount of field enclosed by the loop starts decreasing. Now, the loop doesn't really want this to happen. So in order to prevent the magnetic field from decreasing, a current will flow in the loop that will cause a new magnetic field to be created pointing in the same direction. That means that even though there's less magnetic field there, it'll be stronger. So the total flux through the loop will be mostly the same. So we want to create a magnetic field pointing in this direction, which means that the current in the loop will have to go in that direction, that is, anti-clockwise. So B is the correct answer. Question 3. A current-carrying conductor in a magnetic field experiences a force of F. If the strength of the magnetic field is doubled and the current in the conductor halves, what will be the magnitude of the new force on the conductor? Well, I hope you know what equation we'll be using here. It is, of course, F equals, that's right, BI sine theta. So how are we changing this equation now? We're going to halve the amount of current, and we're going to double the strength of the magnetic field. You can see right away that these two are going to cancel out, right? So we're just left with the same force as what we started with. Therefore, our answer is B.